So in this question 7, the first question is on calculation. So we need to work out the mass of zinc in 30 tons of ZnS. We are working in tons. So how much of ZnS is actually zinc? So you need the atomic mass of zinc. There is 1 zinc. Actually, I'm just going to write everything in one go, okay? So the mass of zinc is going to be the proportion of zinc, which is from the periodic table. Zinc atomic mass is 65, and then divided by the 65 plus 32 for sulfur. That is for ZnS, and then times 30.0 tons. That should give you the mass of zinc. So pretty straightforward there for something which is 2 marks, but I guess that's all level for you. Trying to give you some marks here and there, so make sure that you are not giving it away. I run it up to 3 significant figure, but before that I would show it to more precision. The reason I chose it to run to 3 sig fig is because the data given is 1, 2, 3 sig fig. So how much you run off really depends on the data that you've been given, alright? As it is with experimental sciences as well. So ZnS is heated in air, and the fact that you get the oxides, that means it's the oxygen in the air that reacts. Okay, so you will get ZnO and you will get SO2. So immediately you realize that the zinc are balanced, the sulfur are balanced, the oxygen is not balanced. There's 1 oxygen, there's 2 oxygen, so they altogether you need 3 oxygen on the right. You only have 2 oxygen on the right. You want 3? Of course you can. 3 over 2 times 2 is 3. I just like fractions. I'll keep it as fractions. You can multiply the whole thing by 2 and then you get 2. You get 3, you get 2, and you get 2, and it will still be as balanced. Alright? What you cannot do is you cannot change the number at the bottom, because that's the identity of molecular oxygen. That's how oxygen exists at room temperature and pressure. Alright? So what is the environmental problem when you heat ZnS in air? They already told you form SO2, so you need to outline why SO2 is an environmental problem, okay? So SO2 is produced. SO2 can lead to formation of acid rain. So it's not the SO2 that form the acid rain, but the SO2 can lead to the formation of acid rain via the SO3 route. Yeah, okay. So which I'm sure you have learned in environmental chemistry as part of nitrogen and sulfur. So lead to formation of acid rain, which can make soil too acidic for farming, or you can even kill aquatic plant and animals. But I guess it should be enough to just say that it can lead to the formation of acid rain. Alright, so zinc oxide is treated with dilute sulfuric acid. So zinc oxide is a metal oxide. In all level, most metal oxides are what you consider basic oxides. There are a couple of amphoteric oxide. Is zinc oxide a basic oxide? No. I stand corrected. Zinc oxide is not basic oxide. In all level, you actually learn zinc oxide and AO2 oxide. What you call amphoteric oxide. So they react with both acid and bases. So here, you are reacting ZnO with H2SO4. You will get zinc sulfate, which is your salt, and you will get water to balance the equation. When you react with acid, it behaves like a base. When you react with base, it behaves like an acid. So when you react with the acid, it forms salt and water. The Zn and the SO4 balance out. The H2 and the O give you another H2O there. Okay, so every equation you write has to be balanced, yeah? Actually, what do they want? They want the mass of copper in this. So what's the mass of copper in this? Oh, well, I know the percentage of copper in that, okay? So the percentage of copper is going to be 1 copper. Each copper has a mass of 64 gram per mole of copper, divided by the total MR, which is 1 times 64, plus the iron, 1 times 56, plus 2 sulfur, 2 times 32. Make sure you use a square bracket so that you are not confused when you press your calculator. They want the answer in tons, so I keep this in tons. Alright, so 64 divided, well, the bottom bit first. I hope you get 184. So it's 64 divided by 184 times 20.0. I got 6.9565. I am going to run up to, this is given as 3 significant figure. I'm going to run up to 3 significant figure because that is what you call appropriate number of significant figure based on the data given in the question. Not based on what you want, but based on the data given in the experiment or in the question. Okay. Now to tell you the product of the decomposition, so CuFeS2 is heated in air. You get an oxide, and you get dioxide. These are oxygen. There is no oxygen in here. What do you think the thing in the air that reacted with it? Okay, so you gotta think carefully. Yeah, Cu2 plus O2 minus, Fe3 plus O2 minus. Well, this is a molecule, so sulfur dioxide, as you know from contact process, SO2. Yeah. So CuO, based on how the ions recombine, Fe2O3. You need 2 times plus 3, which is plus 6. You need 3 times minus 2, which is minus 6. There's no charge in this ionic compound. I mean, I think you know this because extraction of iron from iron 3 oxide is your case study. Extraction of metal. Alright? Cu, 1 copper, 1 iron, 2 iron. No good. Yeah. So because I have 2 iron there, I don't want to start off by putting half there, so perhaps I can just make it 1. Then I'll have 2 iron. That means I should put 2 there. Then I'll have 2 iron, but now I have 2 copper. I have 1 copper here, so I put 2 copper. Okay, there's 4 sulfur. 2 times 2 sulfur, there's 1 sulfur, so 4 sulfur. How about the oxygen? There's no oxygen here. There's 2 oxygen plus 3, there's 5 oxygen. 4 times 2 is 8. 8 plus 5 oxygen is going to be 13. I want 13 oxygen. 13 over 2 times 2, because it's molecular oxygen, which you cannot change the property. 13. Some people don't like fractions. As I said in the other video, it's really a personal preference. I like fractions that much. But I also know that to have fractions that is confusing. I tend to just use fraction for the last diatomic stuff. Whereas these are more than 2 atoms. That is quite difficult to see. So I just use fraction here because when it's O2, it's really simple to see the fraction, yeah, by balancing how many oxygen atoms I need. Let's say copper 2 oxide can be reduced by heating with carbon. Okay, I hope you know what is reduction. When you heat with carbon, it will get copper. Where does the oxygen go to? Guess what? Why you form CO? Well, when you think about the extraction of iron, we talk about Fe2O3 plus carbon. Get the iron, which come out as molten liquid iron, right, together with your other impurities, called the liquid slag. Okay, and then what you get? You get CO. You get 2 iron. You get 3 there and 3 there. Funny, right? Case study, and then something you need to think about. All right. Number 5. Oh, this is more calculation. All right. So you want to get 300 gram of SiO2. You want to know what is the maximum mass, so that is 100% yield. Only 100% yield will give you maximum mass. Alright, so from the equation, well, I don't actually need to write that. The mole of silicon over the mole of SiO2 is equal to 1 over 1. I hope you can see is 1 mole is to 1 mole. Alright, this will make it really clear. On the right hand side, I will put in the actual amount. Okay, the mass of silicon divided by the MR, well, the relative atomic mass of silicon, which is 28. So this is from the balance equation. This ratio will be the actual amount that is produced divided by the actual amount that is reacted. So there's 300 gram, which is the correct units that you will use. The MR of SiO2 is just 28 plus 2 times 16. So 28 plus 16 times 2, that's 60. So it's just 60. Mass over the MR is the mole of the silicon. Mass over MR, that's the mole of the SiO2. Actual from the balance equation. Okay, so convert your, not convert, but do your maths carefully, and you should hopefully get that as 140 gram. Okay, unit is already given there, so you are fine. If the unit are not given, you got to write the correct unit there. So next up is more calculation. So they want the maximum mass. So this is assume 100% reaction. If you do not get 100% reaction, then you will not get the maximum mass. That's why you get 0.8% because 0.8 because of the percentage yield being not 100%. When you want percentage yield to be 100%, that's when we assume whatever the reaction gives us, they will give us the maximum mass. Okay, we want that. All right, we have silicon dioxide, so we have to compare the mole ratio of the P4 relative to the SiO2. From the balance equation is one of it is formed from 6 of it. Okay, so that's from the balance equation. How about in reality? In reality, you have the mass of the P4 over the molecular mass. So the molecular mass of P4 is 31 times 4 from your periodic table because you have 4 phosphorus atoms. The molecular mass of SiO2 is 28 plus 16 times 2, that is 60 from your periodic table. So what I'm doing here is the actual mole of the phosphorus is the mass in gram over the mR, and then the mass in gram over the mR. Mole, actual mole of phosphorus that are formed, actual mole of SiO2 that has reacted from the balance equation. Okay, so now what I do really is the mass of P4 is 1 over 6 times 300 over 60 times 124. You can bring all that up, and then that's equal to that, and then I bring the 124 up. Okay, do it in 2 steps if you can't see the maths, but do it in 1 step if you can, so that you can cut down on time. Yeah, what do I get? I get 103.33. Here they don't tell you how many significant figure, but seeing how this is 1 to 3 significant figure in the data, I will round it up to 3 significant figure because it's the appropriate number of significant figure based on the question, and this is already given in gram, so I don't have to put down the units again, but if not, you have to put down the units. Alright, next bit is a calculation. Alright, so what do we have? We reduce a mixture of that and that with aluminium. So in case you don't know, that is moly plus 3 times minus 2. The oxygen is in a compound, so it's at minus 2. You have 3 of it. The compound has no charge. Alright, so it's overall 0. There's moly plus 6. That is, well, you should know this case study, extraction of iron from its ore. This ore is called iron 3 oxide, in case you don't know. Alright, it's called iron 3 oxide because it's iron plus 3, oxygen minus 2. Of course, you can also work it out like this, but you case study, right? Extraction of iron from iron 3 oxide using carbon, reduction of carbon in the blast furnace. Okay, so read up in case you don't know, extraction of metal. Molybdenum steel contains 20% by mass of molybdenum. Now you want to make 1000 gram of molybdenum steel. Okay, so when you have 100 gram of molybdenum, 20 gram will be, sorry, when you have 100 gram of molybdenum steel, 20 gram, because 20% of the 100 will be molybdenum. So in this 1000 gram, how much of it will be molybdenum? That's my question. All right, so the mass of molybdenum, in 1000 gram of moly steel, it's going to be 20% by mass, 20 over 100, so that's percentage. How much of that 1000 gram is actually moly? Okay, so 20 divided by 100 times 1000 will give you 200 gram. Alright, here is the moly, but you want the MoO3. Now I have the mass. I know the AR, so I can work out the mole. I want the mass of this one. Do I know the MR? Yes, I can work it out. This is 96 for the moly. Alright, so the AR there is 96. The MR there is 96. Okay, maybe I should show my working properly down there. Maybe it's number 2 then. So the AR of moly is 96 as given already, but the MR of MoO3 is going to be 96 plus 3 times 16. Each oxygen has a mass of 1 mole of oxygen atoms has a mass of 16 according to your periodic table. which you can find oxygen, of course. I leave that for you to do. Alright, so what I'm going to do is I'm going to compare mole ratio. Alright, from that first equation, the mole of MO3 is equal to the mole of MO. Because 1 mole of it give you 1 mole of it, 1 mole of it give you 1 mole of this. Okay, it's just 1:1, which is make it quite simple there. So you want the mass of MO3, therefore mass divided by MR equal to mole. So this is equal to this. I am just following from the left hand side to the left hand side. Mole equal to mass divided by the MR of this. Alright, gotta be careful what you're doing. Equal to the mass of the MO. You know the moly is only 20% by mass of the steel, right? So out of this steel, only 20% of it, only this much is molybdenum. So it's only 200 divided by 96, which is molybdenum. I want to make the mass of molybdenum as the subject. So move 144 to the other side. It will be 144 times 200 divided by 96. Your calculator will show you as 300 gram. And you want the answer to 3 significant figure. That is 3 significant figure. 1, 2, 3. 3 sig fig there. Okay. So yeah, I hope that's alright for you. Yeah.